For centuries, Venus looked like the safest bet in the solar system. Not Mars, Venus. Same size as Earth, same kind of planet, covered in clouds, bright enough to look almost alive. So scientists made what seemed like a reasonable guess. Maybe Venus had oceans, maybe forests, maybe life. This was not just science fiction. Serious astronomers working at serious institutions published serious ideas about what life on Venus might look like. Then one spacecraft flew past it in 1962, and the dream died in a single measurement. But the strange part is not that scientists were wrong. The strange part is how reasonable the mistake looked at the time. Start with what they could actually see. Venus is the brightest object in the night sky after the moon. You don't need a telescope to find it. On a clear night, it's so bright it can cast a faint shadow. Ancient cultures noticed it, named it after gods of love and beauty, watched it move across the sky with a kind of regularity that made it feel somehow trustworthy. When the telescope arrived and astronomers finally turned it toward Venus, they expected detail. They expected to see what they'd seen when they looked at Mars: surface features, color variations, maybe even polar ice caps. Mars had all of that. Mars was readable. Venus gave them nothing, just a featureless white disk, smooth and blank and impenetrable, like looking at a ceiling. No surface, no features, no variation, just clouds. A planet-wide, permanent cloud cover that blocked every attempt to see what was underneath. And this is where the story gets interesting, because the inability to see the surface didn't lead scientists to caution, it led them to imagination. When you can't see something, you fill the gap with the most reasonable thing you can construct. And the most reasonable thing, given everything they knew, was Earth. The clouds themselves became evidence. On Earth, clouds mean water. Clouds mean weather. Clouds mean an active atmosphere cycling moisture from surface to sky and back again. So the clouds of Venus didn't seem like a warning, they seemed like a promise. All that cloud cover suggested an enormous amount of water vapor, and enormous amounts of water vapor suggested oceans, huge ones. A planet almost entirely covered in warm, shallow seas. The popular image of Venus in the early 20th century wasn't a dead rock. It was a jungle world, warm and wet and teeming, a kind of primordial Earth, locked in an earlier stage of planetary development. The kind of place Earth might have looked like hundreds of millions of years ago, before things cooled and the continents settled into their current arrangement. Science fiction ran with this. Writers described Venus as a place of swamps and ferns and enormous reptiles, a perpetual greenhouse where evolution was still working through its early drafts. And while science fiction isn't science, the underlying logic wasn't invented by novelists. It came from actual scientific reasoning. The swamps of Venus were, for a while, a reasonable hypothesis. Here's what nobody could measure from Earth, and why it mattered so much. Temperature. You'd think this would be obvious, just point a thermometer at it. But temperature measurement at a distance is not the same as temperature measurement up close. You can measure the temperature of the cloud tops. You can figure out roughly how much radiation the planet absorbs and re-emits. What you cannot do, from Earth, is figure out what's happening on the surface underneath those clouds. The cloud tops of Venus are cold, around -40 degrees Celsius, depending on altitude. Point a telescope at Venus and measure the infrared radiation coming off it, and you get a reading that suggests a cold planet, which, paradoxically, also seemed compatible with liquid water, just a different kind. Maybe Venus was cold and icy rather than warm and tropical. Both models, tropical Venus and frozen Venus, coexisted in the scientific literature for decades because nobody had the data to choose between them. What they shared was the assumption that whatever was down there was survivable. Harsh, maybe. Unusual, certainly. But not fundamentally hostile to the existence of liquid water or life. This wasn't bad science. This was science operating at the edge of what was measurable. The mistake wasn't carelessness. The mistake was optimism dressed up as inference. The first real cracks appeared in the 1950s. Radio astronomy, using radio waves instead of visible light to observe the universe, was just becoming sophisticated enough to study planets. And when astronomers turned radio telescopes toward Venus, they got a reading that didn't make sense. The radio emissions coming from Venus were intense. Too intense. Depending on how you interpreted the data, they suggested surface temperatures not in the range of anything hospitable, but in the range of several hundred degrees Celsius. Hundreds. Not warm, not tropical, not the edge of habitable, genuinely, lethally hot. There was immediate resistance to this reading. It was too far from what everyone expected. Some argued the radio readings were being generated in the upper atmosphere, not on the surface, that Venus had an unusual ionosphere producing radio noise, and that the surface beneath it could still be reasonable. This interpretation wasn't crazy. Planetary ionospheres do generate radio emissions. It was a defensible position. Others took the temperature readings seriously and began working through the implications. If the surface of Venus was really that hot, then the cloud cover wasn't a sign of water. It was a sign of something else entirely. Some other atmospheric chemistry, doing something Earth's atmosphere doesn't do. The scientific debate was real. The numbers were contested. And then, in 1962, something happened that made the debate irrelevant. The Mariner 2 spacecraft flew past Venus. It was the first successful interplanetary mission in history. A small probe, not much to look at, launched by NASA on a trajectory that would take it close enough to Venus to take actual measurements instead of observations from 60 million miles away. It carried instruments designed to measure temperature, magnetic fields, and the composition of the atmosphere. The temperature readings were unambiguous. The surface of Venus was around 425 degrees Celsius. Other measurements would later refine this upward to somewhere in the range of 465 degrees. Hot enough to melt lead. Hot enough to melt zinc. Hot enough that any liquid water on the surface wouldn't just evaporate. It would never have been able to form in the first place at that temperature. There were no oceans. There were no swamps. There were no jungles or shallow seas or primordial biospheres still working through their early evolutionary experiments. There was just heat. Savage, unrelenting, permanent heat, spread evenly across the entire planet, day and night, poles and equator, everywhere at once. After that flyby, Venus was no longer Earth's twin. It became the planet that proved how wrong a familiar world can look from a distance. But the question that followed the discovery was, in some ways, more interesting than the question that preceded it. Why? Why is Venus this hot? Not slightly warmer than expected. Not uncomfortably warm. Hot enough to melt metal. Hot enough that the difference between the surface and the cloud tops is more than 500 degrees. Hot enough that the planet radiates heat as if something is actively generating it. What happened to Venus? Because the question of why Venus is this temperature leads directly into a set of discoveries that are, if anything, more unsettling than the temperature itself. Venus is almost exactly the same size as Earth. Same mass, same density, same basic internal structure, a metal core, a silicate mantle, a rocky crust, formed from the same cloud of gas and dust as Earth, at roughly the same time, about 4.5 billion years ago. In its early stages, it almost certainly received impacts from icy objects that delivered water, the same way Earth did. The conditions that produced oceans on Earth were, as far as anyone can tell, present on Venus too. There is evidence, indirect, contested, but real, that Venus had liquid water on its surface for perhaps the first 1 or 2 billion years of its existence. Not a certainty, but a genuine scientific possibility. The models of early Venus's climate suggest it could have been habitable. Warm, yes, but not lethally warm. A place where rain fell and pooled and stayed. Then something changed. Or maybe the stranger possibility is this. Maybe something had already changed before we ever had a chance to see it. Venus does not just look dry today. It looks like a planet after a disappearance. The water is almost gone. But the atmosphere still carries a kind of chemical memory. The lighter hydrogen atoms escape more easily into space. The heavier forms of hydrogen are harder to remove. So when a planet loses water over immense periods of time, what remains can look unbalanced, like a fingerprint left behind after the ocean itself is gone. That does not prove Venus once had blue seas like Earth. It does something more unsettling. It leaves the question open. Maybe Venus had oceans for a long time. Maybe it only had steam. Maybe the paradise we imagined was real for a while. Or maybe it was never more than a shadow created by missing data. Either way, Venus is not just a hot planet. It is a planetary crime scene where the victim may have been water. The sun got brighter. Stars are not constant in their output. They grow gradually more luminous over time as the nuclear reactions in their cores shift. The early sun was about 70% as bright as it is today. Over billions of years, it increased. For Earth, this was manageable. Earth's carbon cycle, a planetary-scale chemical feedback system, adjusted. Carbon dioxide gets pulled out of the atmosphere by weathering and by organisms, locked into rocks and shells and ocean sediments. When the planet gets too warm, more weathering happens. More carbon gets pulled down, and the greenhouse effect weakens. The planet cools itself. Venus lost this ability, or never developed it properly, or developed it and then lost it when the temperature crossed a threshold. The leading theory is something called a runaway greenhouse effect. As the sun grew brighter, Venus got warmer. Warmer temperatures increased evaporation. More water vapor in the atmosphere meant a stronger greenhouse effect, which meant more warming, which meant more evaporation. A feedback loop with no exit. The oceans didn't just evaporate slowly over time, they cascaded upward. Water vapor flooded into the atmosphere. The greenhouse effect intensified. Temperatures climbed. At high altitude, exposed to ultraviolet radiation from the sun, the water molecules broke apart. Hydrogen, the lightest element, escaped into space, lost forever. Oxygen combined with surface rocks. The water was gone. Not stored somewhere, not frozen at the poles, just gone, permanently, destroyed by physics that had no mechanism to reverse itself once it started. Venus didn't drift away from habitability, it fell off a cliff. What's left in the atmosphere is almost entirely carbon dioxide, 96%. The remaining 4% is mostly nitrogen, with traces of sulfur dioxide and other compounds. There is almost no water vapor, almost no oxygen. The atmospheric pressure at the surface is 90 times Earth's, the equivalent of being nearly a kilometer underwater, in terms of the force pressing down on you from every direction. The clouds that blocked every telescope for centuries are not water clouds. They're made of sulfuric acid. Dense, continuous layers of sulfuric acid droplets stretching across the entire planet, reflecting sunlight back into space, which is why Venus looks so bright from Earth, while trapping heat below. The planet is covered in a reflective acid shroud, sitting on top of a surface that would instantly destroy anything made of organic molecules. This is the planet that looked, from a distance, like it should have oceans. The Soviet Union sent probes there. The Venera program, running from the 1960s into the 1980s, was one of the most ambitious and punishing engineering efforts in the history of space exploration. The Soviets were determined to land on Venus and take measurements from the surface itself. The problem was that the surface of Venus is not an environment that engineering is designed for. The first probes were crushed by the atmospheric pressure before they reached the surface. The engineers went back and redesigned them, made the shells thicker, reinforced everything, sent more. Venera 7, in 1970, survived long enough to transmit data from the surface for 23 minutes before going silent. The temperature it recorded was 465 degrees Celsius. The pressure was 90 atmospheres. Later probes lasted longer. Venera 9, in 1975, sent back the first photographs from the surface of another planet. The images showed angular rocks, sharp-edged and unweathered-looking, sitting on a flat gray surface under an orange sky. Not the soft, rounded rocks you'd expect if wind and water had been working on them for billions of years. Sharp, almost fresh-looking by geological standards. Venera 13, in 1982, lasted 127 minutes on the surface, a record, still standing, and sent back color photographs. The surface was yellowish-orange, illuminated by the thick atmosphere filtering the sunlight. Flat rocks, fine soil, a landscape that looked, in some strange way, almost ordinary. Just a surface, just rocks. But at 465 degrees, sitting under 90 atmospheres of pressure, with sulfuric acid clouds overhead, every probe that landed died within a few hours. Not because of malfunction, because of the environment. The heat conducts through the metal, finds the electronics, and shuts them down. There is no way to cool a spacecraft on the surface of Venus, because the heat comes from everywhere and never stops. And yet Venus has one of the strangest loopholes in the solar system. The surface is impossible, but the sky is not. About 50 kilometers above the ground, above the crushed rocks and the glowing plains, the pressure begins to resemble the pressure at Earth's surface. The temperature drops out of the metal melting range and into something almost familiar. Still dangerous, still acidic, still Venus, but no longer instantly impossible. That means the most Earth-like place on Venus is not on Venus. It is suspended above it. In the thick carbon dioxide atmosphere, ordinary breathable air would actually behave like a lifting gas. A habitat filled with the same kind of air humans breathe could float, not because Venus is gentle, but because its atmosphere is so heavy. So the old dream was wrong in the strangest possible way. Venus was not a second Earth on the ground. If anything ever survives there, or if humans ever seriously study it up close, the closest thing to Earth may be a narrow band of sky floating above hell. In 2020, astronomers reported a possible detection of phosphine in Venus's atmosphere, a molecule that, on Earth, almost nothing produces except biology or industrial chemistry. The finding is still contested. The data may have been misread, but the fact that scientists are seriously looking for chemical signatures of life in the clouds of Venus, rather than on any surface, says something. The dream didn't die in 1962. It just moved 50 kilometers up. The surface, when finally mapped by radar in the 1990s by the Magellan spacecraft, was not what anyone expected. Venus has volcanoes, thousands of them. More volcanoes per square kilometer than any other rocky body in the solar system. Large ones, small ones, calderas, lava plains, shield volcanoes stretching hundreds of kilometers across. The surface is geologically young, relatively speaking. Most of the crust appears to have been completely resurfaced by volcanic activity within the last few 100 million years. The old terrain is gone, buried under lava. Earth resurfacing happens gradually, through plate tectonics. Plates move. Old crust descends into the mantle at subduction zones. New crust rises along mid-ocean ridges. The surface renews itself continuously but slowly, over billions of years. Venus doesn't appear to have plate tectonics. Instead, the leading hypothesis is that it undergoes something more catastrophic. Heat builds up in the mantle over hundreds of millions of years, unable to escape through the gradual process Earth uses, until finally the entire surface cracks and floods with lava. A planet-wide volcanic resurfacing event. Then the crust solidifies, and the process starts over. The surface of Venus is not just hostile. It's a product of a completely different kind of geological history than Earth's. Different process, different timescale, different outcome. And yet, the same starting ingredients. The same size, the same mass, the same distance from the same star. Venus rotates backward. Every planet in the solar system orbits the Sun in the same direction, counterclockwise, when viewed from above the solar system's north pole. Most of them also rotate in that same direction. Earth rotates counterclockwise. Mars rotates counterclockwise. Jupiter, Saturn, Neptune, all counterclockwise. Venus rotates clockwise, very, very slowly. So slowly that a day on Venus, one full rotation, takes longer than a Venus year. The planet completes an orbit around the Sun in 225 Earth days, but it takes 243 Earth days to rotate once. The day is longer than the year. Nobody fully understands why. The leading theories involve a collision early in Venus's history, some massive impactor that hit it at just the right angle to reverse and slow its spin, or possibly the combination of tidal forces from the Sun and the thick atmosphere acting together over billions of years to drag the rotation into reverse. The mechanism isn't certain. What is certain is that this rotation has consequences. A slow rotation means the planet doesn't distribute heat well. The same face is exposed to the Sun for enormously long periods. This might have contributed to the instability of the climate. A faster rotation, like Earth's, creates the Coriolis effects that drive weather patterns and distribute heat from the equator to the poles. Venus, rotating so slowly, has nothing comparable. The heat just sits there. One more variable. One more way in which Venus diverged from Earth, despite starting from the same materials. This is the part that should stay with you. Scientists didn't make a naive mistake when they assumed Venus might be like Earth. They made an inference based on every piece of evidence available to them. Same size, same mass, nearby, clouds, thick atmosphere. All the ingredients they knew were associated with life-bearing planets, because Earth was the only life-bearing planet they'd ever studied. The mistake wasn't stupidity. The mistake was a sample size of one. If you have only ever seen one example of something, you naturally build your understanding of what that thing is around that one example. Earth has life. Earth has liquid water. Earth has a moderate atmosphere and mild temperatures and plate tectonics. And all of this works together in a way that has sustained complex life for hundreds of millions of years. When you look at Venus and see the same mass, the same size, the same distance from the Sun, it is entirely reasonable to think it probably shares the other characteristics too. But the characteristics that matter most for a planet's long-term habitability are not mass and size. They're the specific history of what happened to that planet over billions of years. The angle of its axis, the speed of its rotation, whether plate tectonics got started, whether the right kind of carbon cycle developed, whether a large moon showed up to stabilize its orbit, whether the timing of its formation relative to the Sun's evolution gave it enough time to develop life before things got too hot. Dozens of variables, all of which have to fall a particular way, and all of which can only be assessed in hindsight. Venus got most of them wrong. Or rather, from the perspective of any hypothetical biology, Venus got unlucky. The Sun brightened, the feedback loop started, the water left. And there's no way you could have predicted that from the outside, just by measuring Venus's mass. The deeper lesson of Venus isn't about Venus. It's about what it means to look at a planet from a distance and think you know what it is. For 400 years, from the invention of the telescope to the first flyby in 1962, humans looked at Venus and made reasonable inferences that turned out to be completely wrong. Not because of poor reasoning, because reasonable inference, applied to a complex system with a billion-year history, has limits that the universe doesn't care about. This matters now more than it ever has, Because astronomers are detecting planets around other stars at a rate that would have seemed science fiction a generation ago. Thousands of exoplanets, ranging from gas giants to rocky worlds roughly the size of Earth, orbiting stars at distances that put them in what astronomers call the habitable zone, the range where liquid water could theoretically exist. When astronomers describe a planet as potentially Earth-like, they mean similar mass, similar size, similar distance from its star, the same criteria that once pointed at Venus, the same criteria that on their own are insufficient to tell you whether a planet has life, has water, has a livable surface, or is a 465-degree acid-shrouded rock. The lesson of Venus isn't that we were dumb. The lesson is that we were working with the wrong measurements. Size and mass and orbital distance tell you where a planet is. They don't tell you what happened to it, what its rotation rate did to its climate, whether it had plate tectonics, whether its early geological history allowed a carbon cycle to develop, whether the timing of its star's luminosity increase relative to the planet's own development gave it time to build something complex before things got too hostile. To know those things, you need more data. You need to measure the atmosphere. You need to know what gases are present, in what proportions. You need to detect the chemical fingerprints of the processes operating on or in that planet. Telescopes are getting close to being able to do this for nearby exoplanets. The James Webb Space Telescope, launched in 2021, is already collecting light from exoplanet atmospheres and breaking it into spectra that reveal what molecules are there. But Venus should make us humble, should make us hold the hopeful interpretations lightly, should remind us that the gap between what we can observe and what is actually true is enormous, and that the universe doesn't fill that gap with the answer we want. There's one last thing about Venus that tends to get lost in the story of its temperatures and its acid clouds and its crushing pressure. It is extraordinarily beautiful. From Earth, it's the most brilliant point of light in the sky outside of the moon and the sun. Ancient civilizations called it the morning star, the evening star, associated it with the brightest things they knew, goddesses of love and beauty and desire, in culture after culture, independently across the world. There was something in the quality of its light that earned it those names, that put it in that category. The probes that flew through its clouds photographed the upper atmosphere in ultraviolet light, and the images show something extraordinary. Dark streaks and swirls, vast structures hundreds of kilometers long, patterns still not fully understood, some moving at speeds of 350 kilometers per hour, while the planet itself barely rotates at all. The atmosphere is in violent motion, even when the planet beneath it is nearly still. Waves and vortices and structures that look, in some wavelengths, almost alive. The surface, baked and flat and volcanic, glows in its own way. The high temperatures mean the rocks themselves emit infrared radiation, a dull red glow. If you could be there, and you couldn't survive for more than a few seconds, probably less, you would see a landscape lit from above by an orange sky and faintly glowing from below by the heat in the rocks. Completely alien, completely unlike anywhere in human experience. The planet that was going to be paradise turned out to be the closest thing in the solar system to a classical vision of hell. And yet it is also, undeniably, one of the most spectacular physical environments within reach of our telescopes and our probes. It is not what we wanted it to be, but it is something. Sleep well. The universe is full of places nothing like home. Venus was supposed to be the one that was. For a while it was. It had oceans, maybe. A climate that worked, maybe. Something growing somewhere in that early warmth, before the sun brightened and the water left and the feedback loop ran its course. We'll probably never know for certain. What we know is that a planet can look, from the outside, exactly like what you hope it is, and be something else entirely on the inside. We know that now. Venus taught us.